Well, good morning. Oh, here we go. Good morning, ladies and gentlemen. While we fix this problem, I just want to tell you that we're going to be teaching you about nuclear binding energy and some mass defect today. Both Sam and I at the Sam and Kimber show really care about education.
We do. We really care.
Sam, do you think you're okay writing that on the new smartboard?
Oh, dude, I'm doing so well right now.
That is looking pretty nice. Okay, so
gray is just a great color for this background.
gray is a really nice color. Maybe you could take it to red though. That might help.
Oh yeah, we're just gonna
Let's find red.
flip it to red right now.
Meanwhile, let me teach you guys what nuclear binding energy is. For the most part, it's energy released when a nuclide is assembled from individual components. You okay writing that, Sam?
I don't know. I think I'm struggling right now. I don't know what's going on. Oh crap.
Oh my god!
I think we're gonna have to go to a new medium of teaching.
I think you might be right, Sam.
Yeah.
What a brilliant observation. Ladies and gentlemen, we will see you in a few seconds in a new medium.
Sorry, ladies and gentlemen, for that pretty rude interruption, but I think we're back. Sam, let's teach him some physics.
Yeah, let's go. All right. Okay, so here we were left off. We were talking about nuclear binding energy. So nuclear binding energy is basically just the energy released when a nuclide is assembled from its individual components.
Don't forget to get this on your notes, guys. This is really important. But Sam, I think you also need to mention that nuclear binding energy is also the energy required when nucleus is separated into its individual components.
Yeah. I did forget about that. I have to admit it.
It's one of those things, physics is just very advanced, very confusing. Forget a single thing, then, what are you, like, uneducated?
Yeah, that's a struggle for all of us out here in this world. We're just poor souls trying to make our way, and it's just all we have right here is this terrible computer screen.
Mm-hmm.
Yeah.
So what about that mass defect though?
Oh yeah. So then we'll go on to a totally different topic. We'll call this mass defect. Yeah. So
what is that?
So basically, when you're talking about mass defect, you're really talking about the difference between the mass of the nucleus and the sum of the masses of its individual nucleons. So we'll label this delta M, but since I don't know how to do a delta sign, we're just going to put delta M. So yeah, that delta M, that is the difference between the mass of the nucleus and the sum of the masses of its individual nucleons. So
And I think there's an equation that explains this.
yeah, there is So basically, the formula for all of this, if you want to get all numbers up in here, gotta get this mass of nucleus
plus delta M, which I think is actually change in mass, or like how much mass is released or absorbed.
Yeah, it's the mass of nucleus plus the mass defect, and so that's the difference, and that equals the mass of the nucleons. So yeah, there you have it right there. Very interesting stuff. Oh, and remember that the change, this goes back to Einstein, goes back to the great theory of Albert Einstein. Change in energy, delta E equals delta mc squared. Change in mass multiplied by the speed of light.
Which, just from my memory, isn't that 3e to the 8? Give me just a second.
Yeah, basically, man, you got it down. You're a star learner.
Thank you.
So, yeah.
Let's go into the next topic, I think. I think they're ready.
Let's do it.
Remember to copy this in your notes, you guys. So we were about to get on to the next topic, isn't that right, Sam?
Yeah, you're very right.
So, Oh, what's happening? Sam, what's happening? What?
No!
No, what?
This already happened to us today. It can't happen to us again.
It can't happen to us for a second time.
Why is the world like this?
Oh my god. Sam, we might have to use a new medium to teach this material.
A new medium?
Maybe we might have to do marker on a chalkboard.
Remember sideways shot.
Okay, so we're back here on Physics 101. We
couldn't find the whiteboard, but that's okay.
Yeah, but like, it's alright. So we've thrown a lot of concepts at you here today, but we'd like to sort of take a step back and just let you visualize them a little bit. So my man Kimbert here is gonna just draw it out for you.
So our first example is drawing a proton and a neutron coming together. Now, in instances like this, when the proton and neutron are apart, we have a higher energy state. So if this is the proton and this is the neutron, and they're coming together, before they come together, they're both high energy state.
Ooh, very interesting.
Now this is very important to write in your notes, you guys, because this will be on the test.
I'll get you guys a nice close up after
Now.
it's done. Oh yeah, see,
Yes,
there you
look at
go.
that.
Yeah.
Now, we're going to draw what happens after they collide. They form what we like to call a deuteron, which is very advanced, very insane,
Ooh, look at
and that's them together. And usually when this occurs, a photon is released and thus is creating a lower energy state.
No way. You kidding me?
Now,
Lower
Sam,
energy state?
there is another method to this though, and that is when a deuteron, when a photon collides with a deuteron, and that means it goes from the low energy state that we talked about in example 1 to the high energy state, as we saw here in example 2. So I'll demonstrate
Talk
this for
about
you.
putting it in reverse right there.
I know, very advanced. Many people don't know what's going on. So let's say the photon comes in, little photon, just chilling
Chilling on the side.
on the side, and we're going from a low energy state here. We'll just write ES, yeah, because we're cool.
Oh yeah.
Okay, and
You
that,
guys all know what that means. Other people don't, but we do.
yeah, if you're this,
If you're new to this video, you might not know what ES means, but
right.
just gonna help you out.
And then
it's called energy
So
state.
now the proton and the neutron go apart. Okay, it's like magnets almost. Okay,
Yeah, it's like
except it's not.
they don't even want to be together.
We're on the nuclear level though,
Yeah.
and this is a higher energy state.
Definitely.
You might even say the energy between them is not solid.
Ooh. Sneaky joke.
Okay, well I think that is a good place to try an example. What do you think, Sam?
Yeah, let's just give it a shot. Like,
Yeah.
why not?
So I'm thinking, so let's start with, if we have the rest mass equals 1/8, oh, and that's of the deuteron, of course. Deuteron, sorry, the E and the U are backwards, my bad.
E before U, except after D. Man.
1876 MeV per c squared, c negative 2. And those are our units we're going to be primarily using in this section. And our goal is to determine the binding energy and mass defect of this situation. So let's not forget our equation that we talked about in the last segment, which is the mass of the nucleon. Okay, very advanced. Or sorry, mass of the nucleus. My bad, personal foul. Plus delta M equals mass of the nucleon. Okay. Now don't confuse nucleon and nucleus.
Don't do it.
Otherwise you might have a bad time.
Yeah.
Okay, so let's write this out. 1876 MeV per c squared.
1876 was an interesting year, man.
Do you know what? That is true.
Like,
A lot happened.
Like, we could just totally start doing a history lesson about 1876 right now, but I don't think we're going to because we just love physics too
Yeah,
much.
we love physics way too much. Okay. And and I could not forget, but the standard one for a standard charge for a proton in this case is 938 MeV per c squared. And for a neutron, it's 940 MeV per c squared.
Those are very important constants.
Do not confuse these two, otherwise
confuse them.
you may not get the correct answers on your homework.
Yeah.
So in this case, we got delta M equals 2 MeV per c squared. And I did that in my head, okay?
But as you can see, like if Kimber just adds up these two numbers, 938 plus 940, that ends up being 1878 MeV per c squared. So then he just subtracted the 1876.
I just subtracted in this, right?
From the 1878, and then bang, that's your delta M right there. So.
And here we got change in energy equals 2 MeV, and the C canceled out because, or MeVC, right? Because then we multiply that by, remember, change in E equals MC squared. So as you can see, the C's cancel out. Sorry, no C there. That was a my bad.
That's okay. That's okay. Even pros like us get it wrong sometimes.
Yes. And here we have our binding energy.
Oh no!
Oh no!
Oh,
the pencil broke.
Do we have any more pencils?
I don't think we have another pencil.
Oh my god.
You know what, Sam? We might have to find another way to teach this material.
Medium.
A new medium. This is one of the most shocking turn of events of the entire day. We've had so much struggle teaching you guys this material, and I think we are now going to have to find a new medium.
It's really easy material, but like the mediums, they just mess with your head,
Alright,
man.
so here we are in our new medium. Looks like we got some markers and a piece of cardboard. But I'd like to let you know before we start this that we are using 100% biodegradable material throughout this video because we're just trying to save the earth every step of the way. See, like if you check it out right here, it says recycled. So you know what that means. Like, yeah.
Sam, should we teach them about nuclear binding energy per nucleon?
Whoa, dude, calm down a bit. Use your indoor voice right now.
What?
Hey, I'm trying to tell you, you gotta use your indoor voice. It's too loud. It's too loud right now.
I'll just start teaching the binding energy per nucleon plot graph.
All right.
So anyways, folks, well, in the last segment, we showed you that you could actually calculate mass defect and the binding energy. But now we want to really bring you in depth with binding energy per nucleon plot. So typically what we do is we do binding energy here per nucleon.
Naturally.
Per nucleon. Those are the official units, in fact. Okay. And we usually take it out per nucleon number.
Hey, Kimber, what tunes are you listening to there?
Oh, dude, only my brain, because I trust my brain and nothing else.
All right, that's interesting.
And you know what? You might be asking about the fork. That's for the snacks for later. You know, I don't want to be caught off guard in the afternoon with nothing to prepare me for my delicious meal. So I attach a fork with a pin to myself at all times. That way I'm good.
This guy, he's a smart man. Like,
But Sam,
he's the next president.
what about you though? I mean,
I'm doing all right for myself. I actually am a big fan of Chinese food, so like I just go with the double chopsticks on the ears at all times. I mean, it's just one way to stay prepared. Like
mad respect.
anytime you get takeout, like definitely.
Mm-hmm.
So
I think that's pretty sweet.
Yeah.
Let's get back to physics though, you guys. Let's not get distracted.
I mean, like, we all love food, but like we like physics more. Physics is our food.
At the end of the day, physics is what makes us eat.
it sustains us.
Okay, so let's start with 0. Okay, little 0 right here. And we'll maybe go 2. Let's go maybe 4. You know, bring it up 6, 8, 10. You know, it's your classic numbers. Okay.
Yeah.
Let's go 50, hundo, 150.
Ooh, you said that real cool.
And 200. Thank you, Sam. I've been practicing a lot. My mom even tells me I'm special. Okay, so now we're going to start with hydrogen. Let's just do a few little examples. Hydrogen's down here, you know, it has 1 nucleon. Sorry, that's just 1. Has one proton and such, and nucleon.
Yeah.
I think, yeah.
Yeah.
So, you know, the general trend of these, like, it tends to go up for a little bit, maybe go down, maybe up, down. You know, it does some of that, like, you know, and eventually it comes over like this. It just really blows your mind away with a really interesting curve.
Excellent.
In fact, if this
What's at the end of that graph, man?
that's a great question. It's, you know, it's uranium 238.
Ooh,
238.
man.
We'll just write U. And you know what? Just on a side note, if this was a vehicle going through a wind tunnel, this would be a nice aerodynamic shape, except for when it got right in here.
Wow.
But that's a totally separate deal.
Think about that.
That's a whole nother thing of physics. Okay, let's not even get into that. Okay,
Not for this day. Not for this day.
Typically, the one with the highest binding energy per nucleon on most standard graphs.
Oh, it's easily it's a calcium 62 isotope, right?
Right.
No, but like we tend to use iron because like that's just a much more common element in our brains.
It's more accommodating too.
But not calcium, sorry, nickel 62. The nickel 62 isotope, that's straight off the dome right there. But that's
Be
something
sure
I just remember.
be sure to get that in your notes, you guys. You do not want to confuse that. That would be very, very bad. And that's 56, just by the way.
Crucial understanding, crucial.
Crucial. Very crucial. So now we got our hydrogen, which is 2. We got our iron, which is 56.
Yeah.
And we got our uranium, which is 238. That's all you basically need to know. On a side note, too, and this is where it gets cool, okay? Stick with here. Fusion reactions usually occur going this way up to this point, okay? Now, fission reactions occur over here. Now, let's discuss the difference between fusion and fission. I think you guys clearly from this graph understand everything you need to know about this. But I think we should really discuss fusion and fission. So in fission, it's a great question, by the way. Thank you for asking that. Oh, no one asked me? Okay. Well, I'll tell you anyways. Fission, is when a heavy nucleus splits into 2 smaller nuclei of roughly equal mass with the release of energy.
Ooh.
Now,
Keep going.
this can be demonstrated as, like, let's say this is a big, giant mass, like we're coming from uranium, for instance.
Wow.
Okay? And something hits it, something knocks into it,
No way.
and these start splitting apart. Now,
What knocks
I know-
into it?
I know-
What knocks into it? May I ask?
that's a great question. It can be some things as like a,
Could it be a neutron, maybe?
maybe a neutron.
Oh yeah, just
Just a
throw
simple,
a neutron out
simple
there.
little neutron coming in
just
with
a
it.
little neutron, and then boom, you just got World War III, just like
See,
that.
I'm not scared of warfare, but I'm scared of fission.
I'm scared of neutrons.
That's pretty scary.
I'm scared
okay?
of neutrons.
I don't want to be hit by a neutron. Not in my house. Not my kid. Not my kids. Okay? So these things are going to go off in their own way. Very advanced, very insane. But while this occurs, it releases energy and neutrons and different particles depending on which elements you have, what's going on, what type of reaction it is. So just for our case, let's do a U235 example where we're gonna have U235. Sorry, 235. Read that wrong. My bad. 92 plus 1 0 9. And you'll know what this means. I already know you guys know what it means. 56 is pretty advanced. So if you don't understand right immediately, you'll understand later. Sorry, we ran out of room. And this is indicating that there's 3 neutrons, as we demonstrate right here. Plus energy. Pretty sweet.
Yeah.
Okay, now let's. Oh, we're running out of space. Oh, that's a shame. Let's go to the back. Just talk about fusion real quick. Very advanced. And even nowadays, we're still trying to understand fusion and how it works. Typically, fusion is associated with how the sun works. But it's when 2 light nuclei, remember the word's nuclei, it's pretty sweet, combine to form a more massive nucleus with the release of energy. Now, commonly we'll have something where it's like hydrogen, plus like a different isotope of hydrogen. And we get something that looks very cool. Maybe even a helium. That's really what's common in this circumstance.
I like
Feel like a neutron.
alpha particles and stuff like that.
So, lots of different things, lots of different cool. But basically what that is when 2 of these light particles come together and they make
Dang.
a more massive particle, as we see in
That is clear. This particle right here, clearly more massive than these 2 particles.
clearly, as we can
gotta
see
notice
from the
that.
just size. I'll even use the mark to demonstrate this.
Oh wow.
And
It's massive and multicolored.
and that's the main source of the sun's energy, as I already told you. Now, don't get this confused with fission. Remember, fission is the opposite. It goes from this to that.
Yeah. So that's basically what's going on. So that's basically all the concepts we have for today. And Kimber, are you feeling all right, man?
Oh, dude, are these the regular markers? Oh, I'm not feeling too well.
Looks like we're gonna have to take this outside because the best thing for marker-related illnesses is fresh air.
God, So we out here teaching you guys some physics. Sam, let's just whip through the final examples.
Yeah, we're just here in our last medium right now.
So I want to know, what are the similarities between fission and fusion?
Well, that's a very it seems like a simple question on the surface, but if you really break it down and get your hands dirty down here on the sidewalk, it's really a little bit more complex than you think. So, fission and fusion reactions. This is number 2 because it's the second video of our 2-part series. So, fission and fusion reactions. So they have 4 major similarities that they share.
Should we maybe do a little ABCD type deal?
And we'll just knock it out with the ABCD. So number 1, very simple. They both release energy. Obviously, they do that in very, very different manners. But I will say this though, that fission is a lot more common in today's society, nuclear reactors and such. Fusion has not been yet harnessed because of the high temperatures that it takes to reach fusion capabilities.
Hey, can you guys do a wave demo?
What do you think, Sam? Should we do a wave demo?
Well, I mean, like, why not, man? It's like a nice summer day out
It's a
here.
nice summer day. We might as
So,
well do a wave demo.
We're just gonna do wave demo.
Okay, let's go do a wave demo. Sam, what's the first thing we should tell them about waves?
Well, waves, like, when you go to the beach, that's what you're seeing right there in the water. That's waves.
Right.
And, like, other stuff can happen, like light can be waves, sound can be waves, like, all these sorts of things can be waves. But, like, if you really break it down, it's very simple. It's just like this. Oh, crap, I missed. Let's try it again. Oh, see, look.
Did you see that
You see
interference
the
pattern?
vibrations in the water created an interference pattern right there. It was very sly, very subtle, but if camera tries this again, you should be able to see. Oh, see right there? Look at that.
Did you see the wave right there?
It's very. If we gotta slow this video down a bit, but like.
If you put this, like, you know, we can't put it in slow-mo. We don't have that capability, but if you guys put it in
We're
slow-mo
obviously low
by
on
yourselves,
technology skills.
you would be able to see the ripple pattern and the ripple effect. In fact, you'd be able to see the nodes and the antinodes. Now, if we also do a double,
And
like,
this-
interference pattern,
This example is a great example of a longitudinal wave. You see, because a transverse wave is a totally different thing, but a longitudinal wave is it's like sound. So sound travels in a longitudinal wave, whereas light and other things travel in transverse waves. Just a cool tidbit of info right there for you, you know?
I think that's the end of that demo. I wonder if we need any more demos.
Wait, what am I supposed to say?
Oh, did you just ask for a pressure demo?
Can we have a pressure demo?
Oh, okay, let's do a pressure demo.
All right.
Well, I think the best way I can think of, like, a pressure demo is thinking about a can of soda, you know? Like, you've got all that, like, force, you know, pushing from the atmosphere and such on the can, but at the same time you have all that gas and stuff from the carbonation pushing out, you know, in the can. And,
yeah, and like, you're talking about pressure at like 30 FPS or something like that, or 30, whatever unit you measure it in, but like that's just the average atmospheric pressure. And so you see,
what do you think will
pressure
happen
in
when
the
we open
soda
that?
can, well, it bubbles over like that. You see, so the particles in the soda are a lot more excited. They're very gaseous. They're a lot more gaseous than the particles outside the soda. Therefore, we can see that the soda exploded when the soda be opened. So
That sounds like a pretty cool thing.
yeah.
Maybe take a sip. Hot summer day.
A lot of fizz.
And that, ladies and gentlemen, is pressure. Thank you.